Hi everyone. Today we'll be doing the race one from the Infinity Epoch by Secureum Bootcamp. So thanks to Patrick for putting together this website. And now we'll move ahead to the code. So basically we'll have this code and then we'll have 8 questions on it. You can copy paste this code on Remix ID so that you have syntax highlighting and it would be easier for you to read and understand it there. But in the actual races, the code is given just like this without any syntax highlighting. So I would recommend that you try to solve this challenge as it is because that would prepare you to read code in any kind of circumstances. So let's start by understanding the code that we have here. So we have a contract for an Insecurium token. In this contract, first we have a mapping of addresses and UINTs to track balances. Then we have a few variables like decimals, that is 10 to the power 18 for the decimals of the token, total supply for the total supply of the token, and maximum supply or max supply, that is 100 ether. That should be the maximum total supply of this token. Then we have a mint event logging variables like the destination address and the amount that was minted. Next is transfer function. So transfer function takes in a to address and the amount. So basically the address where you want to make the transfer and the amount that you want to transfer. Then we have 3 lines of comments explaining why this snippet was written the way it is. So they're saving the balance in local variables so that they don't have to pay for the S load gas fee on every access. So first you store the balance of the address from which you are making the transfer. Then you store the balance of the address to which you are making the transfer. Then there's a simple check whether the sender has enough amount to send or not. And then you reduce the amount from the sender's account and you add it to the receiver's account safely. The next function is for buying the tokens. So it allows users to buy the token. 1 ether is equal to 10 tokens. So the price is fixed here. This function basically takes in the number of tokens that the user wants to buy. So let's say you want to buy 10 tokens. So you will send a corresponding amount of ether along with your transaction request. So this function is payable as well. So it can receive the ether. Then you do a check of whether enough ether has been sent corresponding to the amount of tokens that you want to buy. If that is true, if you have sent enough ether, those number of tokens are added to the total supply because you are minting new tokens, and those number of tokens are also added to your account balance, and a mint event is emitted. The last function is safe add function. It adds two values and checks for overflows. So when you are adding two values, you can exceed the maximum possible value supported by a UINT, and it basically checks for that. If that happens, it reverts, otherwise it returns the value. So coming to the first question now, to avoid lock of funds, the following features must be implemented before contract deployment. A transfer from function. So if you remember from ERC20 token, a transfer from function allows a third party to transfer the amount from the owner's account to the receiver's account based on the amount that the owner has allowed the third party to spend on their behalf. So a transfer from function wouldn't really help with the lock of funds. So this is false. Next, a burn function. A burn function wouldn't also really help with the lock of funds. So this is also false. A way to withdraw, exchange, or use Ether from the contract. Now, this would help to avoid lock of funds because then we'll have a way to extract Ether from the contract. This could be implemented by adding some admin privileges or adding some ownership to the contract. So, this is going to be true. D, none of the above. So, this is false because C is true. So, the answer for this is C. Now, the next question. Which of the following assertions are true without affecting the security posture of the contract? A. Buy does not need payable keyword. So if we see, this is the buy function. It basically mints new token based on the amount of tokens you need. And you also send the corresponding amount of ether along with the number of tokens that you need. So this function needs to be payable to be able to receive the ether corresponding to which new tokens would be minted. So this is false. Balances must be private. There's really no need for the balances to be private. This is generally done if there's an intention to make the balances private. And anyways, there are no private variables in Solidity. You can always check out the smart contract storage to fetch the values of the private variables. So this is also false. Transfer can be external. Now, for that to be external, we just need to check if no other function in the contract is calling the transfer function, and there's no other function calling it. So it can be external. So this is true. And then safe add can be public. So this is a pure function doing addition with overflow check. So it can be public. So this is also true. The next question, the total supply is limited by 10 to the power 1800 into 10 to the power 1800, none of the above. So we'll go back to the code here. We have a total supply variable and we have the max supply set to 100 ether. So ideally that should be the maximum total supply. But where we are minting new tokens, we are not checking if the total supply is exceeding the max supply we have defined above. So the answer is none of the above. Next, the fourth question. The following issues are present in the code base. A. An integer underflow allows one to drain ether. So there are two aspects to this option. First, you should be allowed to draw ether from this contract. And second, in that logic, some math calculation has to go wrong for an integer underflow to occur. Now, we cannot really draw ether from this contract. Our first question was about that. So this is not going to happen. So this is false. Next is unsafe rounding allows one to receive new tokens for free. So you'll check for where new tokens are being minted and you'll see if unsafe rounding is happening there anywhere. So we'll check the buy function and here we'll see a division operation occurring. Since this is an integer division, it will always return the quotient and not the decimal value. So if you are dividing 10 by 10, you're getting 1. And if you are dividing 15 by 10, then also you are getting 1. So this is where an exploit can happen. So to understand how an exploit can happen, we'll break down the logic with examples. So we have fixed the price that 10 tokens can be minted for 1 ether. Then we check if we have sent the required way for minting the desired amount of tokens. So this is the formula for that. Then we check if we have sent enough ether along with the transaction request to mint the tokens that we need. And if that is true, we add the desired amount of tokens to the total supply and to the sender's balance. Now let's run this algorithm with some actual numbers. So let's say we desire 5 tokens. So for that, the required amount of wave would be 5 divided by 10 into the number of decimals specified in the contract. So that would be 0. So we can get this condition true just by sending 0 ether. So by sending 0 ether, we can mint 5 tokens of this type. In the second example, if you want to mint 10 tokens, the required amount of wave for that would be, according to this logic, 10 divided by 10 into decimals, that is 1 ether. So we'll have to send 1 ether to mint 10 tokens from the contract. And if you look at the third example, if you want 19 tokens minted to us, the required amount of way by this logic would be 19 by 10 into the number of decimals. That is again comes down to 1 ether. So we can mint 19 tokens by sending 1 ether. So this logic is easily exploitable. If we are minting the tokens in the multiple values of 10, we'll have to send appropriate amount of ether. But for any other value, we can send a value corresponding to the lower multiple of 10. You can see the examples here. So we can easily exploit this logic by sending 1 ether and minting 19 tokens, or sending 2 ether and minting 29 tokens, or sending 3 ethers and minting 39 tokens. So this is true. Next, a division by 0 allows one to trap freeze the system. So we'll look where the division is happening. The only place the division is happening is here, and we are dividing by 10. So this is going to be false as well. Sorry, this is going to be false as well. And again, this is going to be false as well because B option is true. So next, fifth question. Now, this question is a really good example of how gas optimization can go wrong if you haven't done it properly. So let's look into it. The following issues is are present in the code base. A. Front running allows one to pay less than expected for tokens. So this is usually done by manipulating the token price while you are executing the transaction. So you manipulate the price such that you get more tokens than you should get. But since the token price is fixed here, you cannot do that. So this is false. A lack of access control allows one to receive tokens for free. Now we'll look at the minting function for this. And there's no access control, but can we get tokens for free? The answer is no. There's one particular case where we can get tokens for free, like we specify we want 9 tokens, but we send 0 ether along with it. So in that case we can get the tokens for free, but in all other cases we'll have to pay some amount. Like I have already explained in the earlier example, this code can be exploited. So if we want 29 tokens, we need to transfer 2 ether. If we want 39 tokens, we need to transfer 3 ether. So we can get the token at a lower rate in a way. But if we mint the tokens between 1 and 9, we can get them by transferring 0 way or 0 ether. So it is not due to the lack of access control, but rather because of the logic that we exploited in our previous question. So this is also false. Now, this is an interesting point. See, incorrect balance update allows one to receive new tokens for free. So, to understand this, we'll see the balance update in the transfer function. So, in this function, we are transferring a particular amount of tokens from the sender's account to the receiver's account. And you'll see here they have done a gas optimization trick that they are pre-storing the balances of the sender and the receiver's account so that they don't have to access them again and again. So they save some gas by not accessing the storage variables again and again. But this logic backfires in a particular case. So the logic of a contract is that we want to send some amount from the sender's account to the receiver's account. We pre-save the balance of the sender and the balance of the receiver from the smart contract storage in local variables. Then we do a simple check if the amount sender wants to send is more than the current balance in their account. And then we do the balance update in the storage variables using the locally saved variables. So we'll take this case by case. In the first case, the sender is transferring some amount of tokens to another address. And in the second case, the sender is transferring some amount of token to their own address. So in the first case, the sender is sending, let's say, 100 tokens to some other account. The sender's current balance is 100. So this gets fetched and stored in the local variable from the contract storage. And similarly, for the receiver's balance, 200 gets fetched and stored in the local variable. The check is passed because sender is trying to transfer 100 tokens and they already have 100 tokens in their balance. Then the balance in the contract storage is updated based on the local variables. So you have 100 minus 100, that is the amount of tokens, and you get 0. So 0 gets stored in the sender's account, and 200 plus 100, 300, this gets stored in the receiver's account. So this goes fine and as intended. But in the case where sender tries to send tokens to their own account, which means they are calling the function with some amount and the to value is the same as the sender's account. So let's say again they are trying to transfer 100 tokens, and since sender and receiver is same, the current balance value is fetched from the smart contract storage and stored in the local variable. The check gets passed because the sender is trying to transfer 100 tokens and they already have 100 tokens. Now, when the balance update happens, the smart contract storage of the sender's account gets updated based on the local variables. So, in the first statement, the balance of the sender's account gets set to 0, that is 100 from the local variable minus 100, that is the amount they are trying to transfer. So it gets set to 0. And in the next statement, since the receiver is the sender as well, it fetches the value from the local variable, that is the receiver's balance here, and it still has the value 100. This is not updated because this we have pre-saved. So it fetches the current balance of the receiver, which is also a sender, from the local variable, and it adds 100 to it. So basically, our sender outsmarts the contract and they get 200 tokens. So that way, a sender can exploit this contract logic by sending the amount of tokens that they already have to their own address and doubling their money. So the sender can send 100 tokens to their own account, they'll get 200 tokens. Then they can send 200 tokens to their own account, they'll get 400 tokens. And then they'll send 400 tokens to their own account, they'll get 800 tokens. So they are doubling money because of this blunder. Talk about 21 दिन में पैसा double. This guy is doubling their money in every 21 seconds. So this option is true, and D, none of the above. This is false because C is true. Sixth question. Following issues are present in the code base. A reentrancy allows one to drain ether. A reentrancy allows one to drain the tokens. A reentrancy allows one to receive new tokens for free. So in all three options, we are talking about reentrancy. And since we are talking about reentrancy, first let's check if reentrancy is possible in this contract or not. So for reentrancy to happen, you need to be making some external calls, and we are not doing that anywhere in this contract. So reentrancy cannot happen. So the correct option is none of the above. The seventh question, following issues are present in the code base. Integer overflow allows one to drain ether. There's no way to drain ether or extract ether out of this contract. This is like the first question itself. So this is going to be false. An integer overflow allows one to receive new tokens for free. So again, from the fourth question, I guess, we can exploit this logic and get some tokens for free. Like if we desire 1 to 9 tokens, we can get them for free. But beyond that, we'll have to pay some amount. Like for 15 tokens, we'll have to pay 1 ether. For 26 tokens, we'll have to pay 2 ether. So beyond 9 tokens, we'll have to pay some amount. So this is not true entirely for all cases. So this is also false. An integer overflow allows one to tap or freeze the system. Now this option is being a little bit too dramatic, but there's no integer overflow happening here that would freeze the system. So this is also false. So since everything is false, the correct answer is none of the above. And the last question of this quiz, question number 8. The Insecurium token contract strictly follows the specification of ERC20, ERC777, ERC721, none of the above. So this is a fungible token. So C option is already out. For ERC20 and ERC777, ERC20 is a standard for fungible tokens, and ERC777 is an enhanced standard in a way for fungible tokens. But this contract doesn't follow any specifications from either of these. So these two options are out as well. You can check more about the specifications of these videos in ETH004 series. There I have a separate video for each of these standards. So you can check out what these standards are there. But for this question, the answer is none of the above. So congratulations, you have solved a race from the Secureum Bootcamp. I hope you have learned something. There were few interesting questions that give you a glimpse of how simple errors can lead to good amount of hacks. So yeah, I hope you learned something. Leave a comment if you have a doubt or feedback. Like, share, and subscribe. And I'll catch you guys in the next.